welcome to this problem walkthrough. Today, we'll be exploring problem number 447, number of boomerangs. This problem is a fun and thought-provoking challenge that involves calculating special tuples of points based on a given distance condition. Stick around as we break it down step by step and discuss efficient ways to solve it. In this problem, you are given a list of points in a 2D plane, where each point is represented by its x and y coordinates. A boomerang is defined as a tuple of three distinct points, labeled I, j, and k, such that the distance between point I and point j is equal to the distance between point I and point k. Importantly, the order of the tuple matters, meaning if you rearrange the points, it will count as a different boomerang. Your task is to calculate and return the total number of boomerangs that can be formed from the given points. The input consists of a nested list where each inner list contains two integers representing the coordinates of a point, and the output is a single integer representing the total count of boomerangs. For the first example, the input is a set of points 0, 0, 1, 0, and 2, 0. Here, we can form two boomerangs. The first boomerang uses the points 0, 0, 1, 0, and 2, 0. This is because the distance from 0, 0 to 1, 0 is the same as the distance from 0, 0 to 2, 0. The second boomerang uses the points 2, 0, 1, 0, and 0, 0, as the distance between 2, 0, and 1, 0 matches the distance between 2, 0, and 0, 0. The output for this example is 2, since we found two valid boomerangs. In the second example, the input points are 1, 1, 2, 2, and 3, 3. Again, we can form two boomerangs based on the same logic as before, and the output is also 2. To elaborate further, for the second example, the two boomerangs are as follows. The first is formed using the points 1, 1, 2, 2, and 3, 3, where the distance from 1, 1 to 2, 2 is equal to the distance from 1, 1 to 3, 3. The second boomerang is formed with the points 3, 3, 2, 2, and 1, 1, where the distance from 3, 3 to 2, 2 matches the distance from 3, 3 to 1, 1. In the third example, there is only one point, 1, 1. Since a boomerang requires three distinct points, it is impossible to form any boomerangs, and the output is 0. This demonstrates how the problem handles edge cases, such as when there are too few points to form valid tuples. The constraints of the problem specify that the number of points, n, can range from 1 to 500. Each point is represented as a pair of integers within the range of -10,000 to 10,000, and all points are guaranteed to be unique. Here are some important considerations. If there is only one point, no boomerangs can exist, resulting in an output of 0. When all points are collinear, boomerangs can still be formed as long as the distances meet the required conditions. The uniqueness of points simplifies the problem, as we don't have to account for duplicates. One key insight is that the order of the points in the tuple matters, so permutations of the same 3 points count as separate boomerangs. To solve this efficiently, we can use a hash map to group points by their distances from a given point, which allows us to count boomerangs in n squared time complexity. To tackle this problem, we start with the brute force approach, which is the most straightforward way to solve it. Here, we examine all possible tuples of points, labeled as I, j, k, and check if the boomerang condition is satisfied. This condition requires that the distance between points I and j is equal to the distance between I and k. The distance can be calculated using the formula x2 x1 2 plus y2 y1 2, which avoids square root operations and keeps calculations precise. While this approach is simple to understand and implement, it has a severe drawback. Its time complexity is n cubed. This cubic complexity arises because we have to iterate over all possible point tuples, making it impractical for larger datasets. To address this inefficiency, we consider an optimized approach leveraging hash maps. Here, the key idea is to count the number of points at each distance from a given anchor point, I. If there are m points at the same distance from I, we can form m*m1 valid boomerangs, as the order of the second and third points matters. This drastically reduces redundant computations by grouping points based on their distances. The optimized approach continues by iterating over each point in the dataset as the anchor point I. For each anchor, we use a hash map to store the frequency of distances from I to all other points. Once the distances are computed and stored, we calculate the number of boomerangs for each unique distance using the formula m*m1, where m is the count of points at that specific distance. Finally, we sum up the boomerangs across all anchor points to get the total count. This optimization reduces the time complexity to O(n) squared, as we compute distances only once per anchor point in O(n) time, and the hash map operations for counting distances are constant time on average. While exploring alternatives, we could consider sorting the distances for each anchor point, but this introduces an additional O log n factor, making the complexity O(n squared * log n. Alternatively, pre-computing a 2D matrix of distances between all points has O(n squared time and space complexity, but it doesn't provide any significant advantage over the hash map approach. Thus, these alternatives are less efficient. After evaluating the options, the hash map-based solution is clearly the best choice due to its balance of time and space efficiency. It leverages the key insight that point order matters, enabling us to count permutations efficiently using frequency data. Additionally, this approach avoids redundant calculations and the potential pitfalls of floating point precision errors by working with squared distances. While it does require O(n) additional space for the hash map per anchor point, this is manageable compared to the inefficiency of the brute force method. In terms of time complexity, the O(n squared achieved by the hash map approach is optimal for this problem, as it minimizes the number of distance calculations without introducing unnecessary complexity. Finally, the code for the hash map solution is relatively straightforward to implement, making it both efficient and easy to understand. For these reasons, the hash map-based strategy is the clear choice for solving the number of boomerangs problem, as it strikes the perfect balance between computational efficiency and implementation simplicity. To solve the problem of finding the total number of boomerangs in a 2D plane, we first need to understand the conditions. A boomerang is defined as a tuple of points, I, j, k, such that the distance between I and j is equal to the distance between I and k. This means the order of the tuple matters, making I, j, k distinct from I, k, j. To calculate distances between points, we use the squared distance formula, which avoids precision issues by not requiring square root calculations. For every point I in the input list, we treat it as an anchor and calculate the squared distance from I to all other points. These distances are then grouped using a hash map, where the keys represent squared distances and the values count how many points share the same distance from I. This setup forms the foundation for counting valid boomerangs efficiently. Now, once we have grouped points by distance for a specific anchor, we calculate the number of boomerangs. If there are m points at the same distance from the anchor, we can form m*m1 boomerangs. This is because for any point j in this group, we can pair it with every other point k in the group, maintaining the order of the tuple. This count is added to the total boomerangs. We repeat this process for all points in the input, treating each one as the anchor. Key insights here include the use of squared distances for simplicity, ensuring the order of tuples is respected, and leveraging a hash map for efficient grouping and counting. These steps significantly reduce the computational effort compared to a brute force approach, which would check all possible tuples individually. The algorithm relies on two main data structures, a hash map to store the frequency of squared distances and a list to represent the input points. The time complexity involves an outer loop that iterates through each anchor point, taking O(n), and an inner loop that calculates distances to all other points, also O(n). Hash map operations, such as inserting and retrieving values, are O(1) on average. This results in an overall time complexity of O(n squared). The space complexity is determined by the hash map, which stores distances for each anchor point, requiring up to O(n) space. Therefore, the algorithm is efficient with both time and space, making it suitable for inputs with up to 10,000 points. The implementation begins by initializing a hash map and iterating through the list of points. In the implementation, for each anchor point, we calculate the squared distance to every other point using the formula dx(2 plus dy(2). These distances are stored in a hash map, where the keys are the squared distances and the values are their frequencies. If a point is the same as the anchor, it is skipped to avoid self-comparisons. After populating the hash map, we compute the number of boomerangs by iterating through the frequency values in the hash map. For any distance with more than one point, we add count*, count 1, to the total boomerang count. This ensures every valid ordered pair of points is considered. Finally, the total number of boomerangs is returned. The algorithm also handles edge cases, such as when all points are the same, when no boomerangs exist, and when the input size is large, ensuring it operates efficiently under all constraints. To illustrate how the algorithm works, let's walk through an example with points 0, 0, 1, 0, 2, 0. When the anchor is 0, 0, the squared distances to other points are 1, 1, 4, 1, resulting in 0 boomerangs since no distance has more than 1 point. For the anchor 1, 0, the distances are 1, 2. With 2 points at the same distance, we calculate 2 asterisk, 2 to 1 equals 2 boomerangs. Lastly, with 2, 0 as the anchor, the distances are again 1, 1, 4, 1, yielding 0 boomerangs. Summing these results gives a total of 2 boomerangs. This example demonstrates how the hash map efficiently groups distances and counts valid tuples, validating the algorithm's correctness and performance. This Python implementation solves LeetCode problem number 447, number of boomerangs. The goal is to count all boomerangs, which are tuples of points that satisfy the distance condition. We begin by importing defaultic from collections to maintain a count of distances efficiently. The main function, number of boomerangs, takes a list of points as input. The variable total underscore boomerangs is initialized to store the total number of valid boomerangs. For each point I in the input list points, we create a dictionary distance underscore count using defaultic int. This dictionary will store the frequency of distances from I to every other point j. Next, we iterate through all points j. If point I is the same as j, we skip it. Otherwise, we calculate the squared distance between I and j using the formula dx asterisk dx plus dy asterisk dy. Squared distances are used instead of actual distances to avoid unnecessary floating point operations. We then increment the count of this distance in the distance underscore count dictionary. After processing all points j for a given point I, we iterate over the values in distance underscore count. For each distance that occurs more than once, we compute the number of boomerangs using the formula count asterisk, count 1. This formula accounts for all possible permutations of 2 points, j, k, that are equidistant from I. Finally, the total count of boomerangs is updated by summing these values, and the result is returned at the end of the function. The algorithm has a time complexity of O, n squared, where n is the number of points, as we iterate through all pairs of points. This solution is efficient for the problem's constraints. Here, we start by importing the necessary libraries and defining our solution class. The method number of boomerangs takes a 2D array of points as input and initializes a variable total boomerangs to 0. This variable will keep track of the total number of boomerangs we find. Next, we use a nested loop to iterate through each point in the array. For each point I, we create a hash map called distance count to store the squared distances between point I and all the other points. The squared distance is used here to avoid issues with floating point precision when working with actual distances. Inside the inner loop, we skip the calculation if the point j is the same as point I. Then, we calculate the squared distance between points I and j using their x and y coordinates, and we update the hash map with the distance as the key and its count as the value. This allows us to track how many points are at the same distance from the current point I. Once the inner loop is done, we process the distance counts in the map to compute the number of boomerangs for this point. For each count in the distance count values, we check if the count is greater than 1. This is because at least 2 points are needed to form a boomerang with the current point. If the condition is met, we calculate the number of boomerangs using the formula count asterisk, count 1, which is derived from the permutation formula for selecting 2 points out of count points. These boomerangs are then added to the total boomerangs variable. After processing all points and their respective distances, we return the total boomerangs value, which represents the total number of boomerangs in the input set of points. This implementation is efficient and leverages the hash map to group distances, ensuring that the calculation remains manageable even for larger datasets. To solve the problem, we start with the first example where the points are 0, 0, 1, 0, 2, 0. First, we initialize a variable total underscore boomerangs to 0, which will store the total count of boomerangs. We then iterate over each point, treating it as the anchor point I. Starting with I equals 0, 0, we initialize a dictionary distance underscore count to keep track of the frequency of squared distances from I to other points. For j equals 0, 0, we skip the calculation since I is the same as j. For j equals 1, 0, we calculate the squared distance as -1, 2 plus 0 squared equals 1 and update distance underscore count to 1, 1. For j equals 2, 0, the squared distance is calculated as -2, 2 plus 0 squared equals 4, and we update distance underscore count to 1, 1, 4, 1. After processing all points, we look at the frequency of each unique distance. For distance 1, the count is 1, so no boomerangs are possible. Similarly, for distance 4, the count is also 1, resulting in no boomerangs. At this stage, the total remains 0. Next, we set the anchor point to I equals 1, 0 and reinitialize distance underscore count. For j equals 0, 0, the squared distance is 1, so we update distance underscore count to 1, 1. For j equals 1, 0, we skip the calculation since I is the same as j. For j equals 2, 0, the squared distance is 1 again, and we update distance underscore count to 1, 2. Now, we check the unique distances. For distance 1, the count is 2. Using the formula count asterisk, count 1, we calculate 2 asterisk 1 equals 2 boomerangs and add this to the total, making total underscore boomerangs equals 2. Finally, we set the anchor point to I equals 2, 0, and repeat the process. For j equals 0, 0, the squared distance is 4, so distance underscore count becomes 4, 1. For j equals 1, 0, the squared distance is 1, updating distance underscore count to 4, 1, 1, 1. For j equals 2, 0, we skip the calculation. Checking each distance, both distance 4 and distance 1 have a count of 1, so no additional boomerangs are added. The final total for this example remains 2. In the second example, the points are 0, 0, 1, 1, 2, 2, and we again initialize total underscore boomerangs to 0. Starting with the anchor point I equals 0, 0, we initialize distance underscore count. For j equals 0, 0, we skip the calculation as I equals j. For j equals 1, 1, the squared distance is -1, 2 plus -1, 2 equals 2, so we update distance underscore count to 2, 1. For j equals 2, 2, the squared distance is -2, 2 plus -2, 2 equals 8, and we update distance underscore count to 2, 1, 8, 1. Checking each unique distance, both distances 2 and 8 have counts of 1, so no boomerangs are added. The total remains 0 at this point. Now, with the anchor point set to I equals 1, 1, we reinitialize distance underscore count. For j equals 0, 0, the squared distance is 2, so distance underscore count becomes 2, 1. For j equals 1, 1, we skip the calculation since I equals j. For j equals 2, 2, the squared distance is also 2, updating distance underscore count to 2, 2. For the unique distance of 2, the count is 2, and using the formula, we add 2 asterisk 1 equals 2 boomerangs to the total, making total underscore boomerangs equals 2. Finally, with I equals 2, 2, we repeat the process. For j equals 0, 0, the squared distance is 8, so distance underscore count becomes 8, 1. For j equals 1, 1, the squared distance is 2, updating distance underscore count to 8, 1, 2, 1. For j equals 2, 2, we skip the calculation. Both distance 8 and distance 2 have counts of 1, so no additional boomerangs are added. The total for this example remains 2. In the third example, the points are 0, 0, 1, 0, 0, 1, 1, 1. We initialize total underscore boomerangs to 0 and start with the anchor point I equals 0, 0. Initializing distance underscore count, we skip j equals 0, 0 since I equals j. For j equals 1, 0, the squared distance is 1, so distance underscore count becomes 1, 1. For j equals 0, 1, the squared distance is 1 again, updating distance underscore count to 1, 2. For j equals 1, 1, the squared distance is 2, and distance underscore count becomes 1, 2, 2, 1. Checking unique distances, for distance 1, the count is 2, so we add 2 asterisk 1 equals 2 boomerangs. For distance 2, the count is 1, so no boomerangs are added. The total so far is 2. Next, with the anchor point I equals 1, 0, we reinitialize distance underscore count. For j equals 0, 0, the squared distance is 1, so distance underscore count becomes 1, 1. For j equals 1, 0, we skip the calculation. For j equals 0, 1, the squared distance is 2, updating distance underscore count to 1, 1, 2, 1. For j equals 1, 1, the squared distance is 1, and distance underscore count becomes 1, 2, 2, 1. For distance 1, the count is 2, so we add 2 asterisk 1 equals 2 boomerangs, making total underscore boomerangs equals 4. For distance 2, the count is 1, so no boomerangs are added. Similar calculations for I equals 0, 1, and I equals 1, 1 yield additional boomerangs, bringing the final total for this example to 8. To analyze the time complexity of this algorithm, we start by examining its structure. The algorithm uses a nested loop to iterate over the list of points. If there are n points in total, the outer loop runs n times, as it processes each point one by one. For each iteration of the outer loop, the inner loop also runs n times, as it compares the current point with all other points in the list. Within this inner loop, the algorithm calculates the squared distance between 2 points using basic arithmetic operations, such as subtraction and multiplication, which take constant time, or O(1). Additionally, the algorithm updates a hash map to store the frequency of distances. These updates, like adding or incrementing an entry in the hash map, also take O(1) time on average. Together, these steps contribute to the overall efficiency of the algorithm and lay the foundation for a deeper analysis of its time complexity. After processing all points in the inner loop for a specific point, the algorithm performs an additional step to count the number of boomerangs. It iterates over the entries in the distance underscore count dictionary, which stores the frequency of distances for the current point. In the worst case, where all points are equidistant, the dictionary might contain up to n unique entries. This means the loop over the dictionary could run up to O(n) times for each point. When we combine all these factors, the overall time complexity can be broken down as follows: the outer loop runs O(n) times, the inner loop runs O(n). For each iteration of the outer loop, operations within the inner loop take O(1), and counting boomerangs adds another O(n) step per point. Adding these together, we get a total time complexity of O(n) squared plus n squared, which simplifies to O(n) squared. This is a significant improvement over a brute force approach. Now let's examine the space complexity of the algorithm. The primary data structure that contributes to space usage is the distance underscore count dictionary, which is created for each point I to store the frequency of distances to other points. In the worst case, if all distances are unique, the dictionary could have up to n entries. Each entry consists of a key, which is the distance value, and a corresponding frequency value, both of which are integers. Therefore, the space required for the dictionary in the worst case is O(n). Apart from this, the algorithm uses a few scalar variables, such as total underscore boomerangs and the loop variables, which consume constant space, or O(1). It's important to note that the dictionary is recreated for each point and does not persist across iterations, so the overall space complexity remains O(n). This ensures that the algorithm is efficient in terms of both time and memory usage. Finally, let's analyze the algorithm across different scenarios. Regardless of the arrangement of the points, the time complexity remains O(n) squared in the best, average, and worst cases because the algorithm must compare every pair of points. The worst-case scenario occurs when all points are equidistant, which maximizes the size of the dictionary for each point, but this does not change the overall complexity. To highlight the efficiency of this approach, we can compare it to a brute force solution. A naive method would involve generating all possible triplets of points, which requires O(n) cubed time, as each triplet would need to be checked for the boomerang condition. The current solution avoids this by using a hash map to count distances, reducing redundant calculations and improving the time complexity to O(n) squared. Mathematically, this complexity arises from the nested loops over the endpoints, with inner operations like distance calculation, hash map updates, and boomerang counting being either O(1) or linear in the number of unique distances. This makes the O(n squared) pairwise comparisons the dominant factor in the algorithm's performance. In this section, we'll discuss some common mistakes to watch out for when solving the number of boomerangs problem. First, many solutions fail to handle duplicate points correctly. If your input contains duplicate points, you might unintentionally count invalid tuples. To address this, make sure to explicitly skip or handle duplicates during your computations. Next, another frequent error arises in calculating distances. When computing the squared Euclidean distance, you must square the differences in both x and y coordinates, rather than taking the square root. Using the square root function is unnecessary here, and it can introduce precision errors, especially in integer-based problems. Another issue occurs when generating tuples. It's essential to ensure that the indices in your tuples satisfy the condition I equals j and I equals k. Failing to enforce this can result in counting invalid or redundant tuples. Finally, while a brute force triple nested loop might work for small inputs, it's highly inefficient for larger constraints. Instead, optimize your approach by leveraging hash maps or other data structures to reduce the time complexity and avoid exceeding time limits. Now, let's consider a few more important points. For example, inputs with fewer than 3 points are an edge case that you should handle explicitly. In such cases, the result is always 0 because it's impossible to form a valid boomerang with less than 3 points. Neglecting this scenario can lead to runtime errors in your solution. Shifting focus to interview insights, one key takeaway is that problems involving distances between points often benefit from pre-computing and storing distances in hash maps. This approach can significantly reduce complexity, bringing it down from O(n cubed) to O(n squared). Additionally, recognizing the problem's pattern is helpful. It belongs to the category of geometric problems with constraints. These often offer opportunities to avoid redundant work through techniques like symmetry or pre-computing values. As you optimize, consider using dictionaries or sets to track distances and streamline comparisons. Be mindful of edge cases, such as duplicate points, minimal input sizes, and large constraints. Lastly, during interviews, clearly explain why a brute force approach is inefficient and how your optimized solution minimizes redundant computations. Highlight the computational trade-offs you made to justify your choices. To deepen your understanding, let's look at related problems. LeetCode 149, max points on a line, shares a similar concept as it involves comparing geometric properties, specifically slopes, between points. Another related problem is LeetCode 18, for some, which focuses on generating tuples and optimizing their computation using hash maps. Additionally, LeetCode 287, find the duplicate number, emphasizes the use of map-based strategies to detect duplicates, which parallels some aspects of handling duplicate distances in the number of boomerangs problem. And of course, LeetCode 447 itself is a direct example. Revisiting and practicing these problems can help you solidify your understanding of tuple generation, distance-based computations, and optimization techniques. Finally, let's explore some alternative approaches to solving this problem. A brute force approach, while simple to implement, has a time complexity of O(n cubed), and is only practical for small input sizes. It's not efficient for larger constraints due to the sheer number of computations. A more practical solution is the optimized hash map approach, which reduces the complexity to O(n squared). This method avoids redundant calculations but does require careful management of the hash map. Another option is a sorting-based approach, which typically has a time complexity of O(n squared * log n). This involves additional pre-processing but can simplify certain lookups. However, it's not always the best fit for problems centered on distance calculations. Lastly, there's the divide-and-conquer strategy, which is rarely used in this context. This method can achieve a complexity of O(n * log n, depending on how it's implemented, but its complexity makes it less suitable for standard distance-based problems. Understanding these trade-offs allows you to select the best approach for the given constraints and problem requirements. Great job following along. To summarize, we tackled the problem by exploring both brute force and optimized approaches. We learned how hash maps can help manage frequency data efficiently and reduce computational complexity. These are crucial concepts for solving problems in interviews. Thank you for watching, and don't forget to like, subscribe, and share this video. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!